Question 4 introduces mass spectrometry, which is very different from infrared spectroscopy, but what it does, like infrared, is provides valuable clues that can help you in figuring out what the structure of a molecule is, although again, like infrared, it doesn't actually tell you what the whole structure is. It's different from other kinds of spectroscopy, like infrared, in that it doesn't involve interaction of molecules with electromagnetic radiation, with light or infrared or whatever. It is really just a method of measuring the mass of individual molecules, or atoms sometimes. But that's obviously a very challenging thing to do because they have very small masses. You can't just stick them on a balance because the mass is far too small for that. So you don't really need to know how it works, but it's worth just having a simple picture in your head of what's going on in a mass spectrometer. They actually come in lots of different varieties, but the simplest one, which is what I'll briefly describe, is called a time of flight mass spectrometer. So the idea is that you have, first of all, what's called an ionisation device. Now, these come in lots of varieties. There are lots of different ways of ionising your molecules, but the key thing is that one way or another, what this does is turns the molecules into positive ions. Usually by simply knocking one electron out of the molecule to turn it into a positive ion. And that's very important because neutral molecules, it's very hard to control the way they move because you haven't got a handle on them. As soon as you generate a positive ion, you can use an electric field or sometimes a magnetic field to get them to move in a defined way. And so the creation of ions is crucial, and the consequence is that everything to do with mass spectrometry is about positive ions, and that's going to become important when you come to writing your answers, because when you talk about the species flying through a mass spectrometer, you always need to show that they're positive ions. So that's the starting point. Now what you then have is some kind of device which will draw like this, and basically this is called an accelerator or acceleration section. And the idea is that you put increasing negative potential here, and that's obviously going to attract these positive ions out of there, and as they move through this electric field, moving towards increasing negative charge, they're going to be accelerated. So what emerges from here is a beam of positive ions. Now the clever bit is what goes on in here, because if we assume that all our ions have just a 1+ charge, that won't always be true, and in real life that can be a complication but also sometimes an advantage. But for A-level purposes, it's easiest just to think of the ions as always having the same charge, a 1+ charge. Then what that means is that the electric field will apply exactly the same force to all of them, because the force just depends on the charge on the ion and the size of the electric field that is interacting with. So there's the same force applied to them. And if you remember Newton's second law from physics, force equals the mass times the acceleration, and if we just rearrange that, acceleration equals force over mass. So if the same force is being applied to all of the ions, then what you can see is that the bigger the mass of the ion, the smaller the acceleration will be. And that's the key thing, because what it means is that these ions emerging from here will all be travelling at different speeds, and the ones with the smallest mass will be travelling fastest, and obviously the ones with the biggest mass will be travelling slowest. And what you measure is the time of flight between here and somewhere up here, where you have a detector. Okay, so this is called a drift tube because through here the ions are just moving. They're not being accelerated anymore because there's no electric field, and they will move at a constant velocity, but each will have its own velocity depending on how much it was accelerated there. So you measure the time of flight through this tube, which is the time taken between the end of the accelerator and where it's detected. So that's one type of mass spectrometry, which is time of flight mass spec. Now, as I say, you don't need to know any of that, except that you need to know that the technique depends on generating positive ions, and what it actually measures is not the mass of the molecule, but the mass of a positive ion. Now, if you remember, the mass of an electron is very small. It's about 1/2000th of the mass of a proton or a neutron. And so removing one electron from a molecule makes a negligible difference to the mass unless you're working to incredibly high resolution. And at the level we're working at, that loss of an electron makes no significant difference. So effectively, the mass of the positive ion we measure is the same as the MR. And that's the basis of the method. Okay, so what a mass spectrum looks like is a graph, and what goes along the bottom is written as m over z, which means mass divided by charge. The point about that being that in the actual experiment you may have ions with different charges, and as you can imagine, if you have a 2+ charge, that's going to interact more strongly with the electric field and so get accelerated more than an ion with a 1+ charge. So that's why you can't just directly plot mass down there, because it depends on the charge of the ion as well. For A-level purposes, we don't worry about that complication. So you can just think of this as being equivalent to the mass, but you need to know that it's m over z, mass over charge. But in terms of the numbers, it's going to be the same as the mass. And rather than represent it in grams or any units like that, because we're interested in chemical entities, we use the MR scale. So this is going to have numbers along the bottom which are basically going to be the same as the MR of the fragments that we measure. And what goes up here is abundance, which just means how many of those ions there are in your sample. So the idea is that when an ion reaches the detector, it generates some kind of electrical signal, and the more ions of a given mass, they're all going to reach the detector at the same time, and the more of them reach the detector, the bigger that signal will be. So you can relate the size of the signal detected by the detector actually to the amount of each ion you've got. So what you get in a mass spectrum is a series of peaks with different masses corresponding to the different masses of the species in there, but the size of those peaks is a measure of how much of each substance there is, and in some applications that can be very important because you can actually use it as an analytical method to quantify the amounts of different substances in your sample. So before we get on to the actual question, let's just look at a very simple example of that by taking a diatomic molecule like say nitrogen, okay, which is N2. So the first thing to remember is that an N2 molecule can't do anything in a mass spectrometer because it has no charge. It must have a positive charge. So the first thing you do in a mass spectrometer is generate N2+. And when you're writing about mass spectrometry, it's really important always to remember to show those positive charges on there. Or, you know, we could write it like this if we wanted to show the bonding. And what I normally do is put a square bracket around it and put the charge outside, because that way you're not pinning yourself down as to where exactly the charge is. Okay, so because nitrogen only has one common isotope, which is nitrogen 14, all of the molecules will have essentially the same mass, just barring those tiny number that have a different isotope, which is 14 for each nitrogen and therefore 28 for that species. And therefore we will get a peak with an m/z value of 28 corresponding to N2+. Okay, so you can see 28 is the MR of N2, so you get a peak at 28, but what you're actually detecting is not N2 molecules, but N2+ ions. And the term we use for those are molecular ions. Okay, so this is called the molecular ion peak. And that's going to be probably the single most important kind of peak to us in terms of our A-level use of mass spectrometry. So the molecular ion peak, which means that it arises from the intact molecule minus 1 electron. So we're going to be looking for the molecular ion peak in our organic mass spectra because it can give us the MR, and that is incredibly useful information. Depending on what sort of ionization technique you use, what you will also tend to get is that some of these N2 molecules will fall apart, and so you get a fragmentation process like this where N2+ falls apart to give you N plus N. Okay, so the ion is just breaking up into atoms. That we can't detect because it has no charge, but this of course we will detect, and it will fly through the mass spectrometer, and because it's just a single atom, that will give you a peak at 14. Okay, which is N+. Now these kind of peaks are very important in organic spectra because the mass difference between the intact molecule and the fragment tells you what's dropped off, and that can often be very insightful in terms of what sort of groups there are there, and we'll see examples of that when we get on to the detail. So this is called a fragment ion, and we'll look at how those can be useful in a bit. Okay, so that's the general background. So now let's have a look at what's going on actually in question 4. Okay, so here's the mass spectrum that it shows us in question 4. So the first thing to go looking for always in mass spectrometry questions is the molecular ion peak, which remember is due to the intact molecule just minus 1 electron. And it's going to be easy to find because it's going to have a bigger mass than any fragments that result from it breaking down into bits. So if it has the biggest mass, the ion it generates will have the biggest m/z value. So what you do is you just look through for the peak that comes furthest to the right, and it's the peak there that's labelled with the star. So that's called the molecular ion peak. There is, if you notice, a little tiny peak there with a mass unit 1 bigger than that. We'll talk about that in a minute, but that's actually not the molecular ion peak that we're interested in, or it's a type of molecular ion peak, but not the main one. So we're looking at this peak here. So that's the molecular ion peak because it's the one furthest to the right. Notice it's not necessarily the tallest peak, because often you find that a majority of molecules fragment. So the molecular ion peak may be, one of the smaller peaks. So this one, there's much more of this fragment than there actually is of the intact molecule. That's perfectly normal. So when you're talking about the molecular ion peak, make sure you explain it's not necessarily the biggest peak, but it's the peak with the biggest m/z value is what we're talking about here. So what you do is explain then that m/z is equal to 46 for the molecular ion peak, and that just means that the MR is equal to 46 for this substance. So it's a very simple and effective way of finding the MR of a substance, which obviously is really, really useful when you're trying to figure out what the structure is. So that's our starting point. Now let's just talk about this peak. Okay, so this is m/z equals 47, and it's sometimes called the m+1 peak. okay, because it has an M over Z 1 bigger than MR. So you think, well, how does that arise? And the answer is that about 1% of carbon atoms are carbon-13, whereas, of course, the common isotope, the overwhelming majority of them are carbon-12. But 1% of carbon atoms, just randomly distributed, happen to be carbon-13. And that means that in a small proportion of molecules, one of the carbon atoms will happen to be carbon-13. Because that has one extra mass unit, it means the molecule that contains it will have one extra mass unit. And so that's what's going on here. That peak at 47 results from the minority population of molecules which happen to have a carbon-13 on board. So this is the carbon-13 satellite peak. And so you learn to ignore it. Okay, so what you generally see with a molecular ion peak is a peak with a significant intensity and then a little tiny one on its shoulder, like that, and you learn to ignore that small peak there. Now, small peaks in general you usually ignore. So these ones, for example, it's often very difficult to explain where those could have come from. Normally, actually, the peaks at 29 and 15 you would probably ignore because, again, they're quite low in intensity, and those peaks are dangerous because they can result from all kinds of things going on that are not easy to explain. So in the context of this question, you're asked to explain them, and we'll see that's quite easy to do. But more generally, it's these kind of peaks, the big tall ones, those are going to be the ones you're going to focus on. Okay, so we've got the molecular ion peak. Got to make sure you remember that term and remember what it means. Intact molecule, except that it's had one electron knocked off it, so it's become positively charged. But the mass of that peak is essentially the same as the MR. So that's the information that we read off. And you explain it like that, that the M over Z is whatever it is, and that means the MR is equal to that value. Now, it tells us in the question that this substance is an alcohol. We might know that, for example, by having done an infrared spectrum, which would have showed that characteristic alcohol OH peak. So it would be quite reasonable that we might know that, and now we know the MR as well. So we can think, right, our alcohol is going to be ROH, where R represents the organic bit that has OH attached to it. And so you can easily work out what the mass of the R group is, because you know that OH has a mass of 17, and you know that the whole thing has a mass of 46. And so you can work out that the R group, whatever the organic group is, has a relative mass equal to 46 minus 17, which is 29. So then you have to think, right, what could that be? And really that comes down, in simple situations where there's only one functional group in the molecule, to counting how many carbons could that be. So if the mass is 29, what you do is you think, right, how many carbons could that be? Remembering each carbon adds up to 12. So if you had one carbon, you would have to have C12, So if you had one carbon, you would have C, which adds up to 12, and then you'd have to have H17OH. And that's obviously ludicrous. You can't have one carbon with 17 hydrogens around it. So that's not possible. If you had two carbons, you'd be C2, takes you to 24, and that gives you 5 more to make 29, H5OH, and that looks fine. If you had 3 carbons, that's too many, because that already adds up to 36. That's too many, because we know that R only adds up to 29. So this is the only possible formula. And of course, because that's a very simple one, there's no ambiguity. With bigger ones, there'd be possible structural isomers to worry about, but with this, there's no ambiguity. That's ethanol. So we're talking about CH3, CH2, OH. And we can tell that just from the molecular ion peak. We didn't actually need any information from the fragments in that case. But because this is an exercise, we can see if we can identify the fragments just to help us understand how this method is useful. Okay, so that's what the molecular ion is, CH3, CH2, OH, but it's got a positive charge because that's what you detect in mass spectrometry are positive ions. So you've always got to remember that when you're describing what the species are. So that's what this peak results from, okay, the molecular ion. So what we're going to do now is to say, well, what about these peaks? And the way you think about that is just to think, well, they result from this ion being unstable. It depends how you create it, but usually it's done by bombarding the original molecules, in this case the ethanol molecules, with some kind of high energy particles like fast moving electrons. And when they crash into these molecules, they can knock an electron out of its orbital, hence this becomes a positive ion. But they also transfer a lot of kinetic energy to this molecule as they crash into it. And that tends to make it unstable and gives it the chance of falling to bits. And when it does that, normally it will just be one single bond that breaks. There isn't usually enough energy to break double bonds, or to break more than one bond at one time. I mean, that's a very generalized rule of thumb, but that's what we're going to work with for A-level purposes. So what we're looking at is fragments that we can generate just by breaking one bond and one bond only. But the complication is that that tends to be random. So in this case, obviously, you know, if we drew that out as a displayed formula, you can see we've got lots of candidate bonds that could be broken, because all of those single bonds are candidates for things that could be broken when that positive ion fragments. If you break one of these bonds to hydrogen, there or there or there or there or there or there or there, you're just going to remove one from the mass. And that can give you a peak at m-1, just loss of a hydrogen. And generally that's not very interesting, in the same way that the CH peak wasn't very interesting in the infrared. Because, okay, it tells you there's a hydrogen in the molecule, but that's not really very useful. Also, actually, the peak's often very small because CH bonds are quite strong and they don't tend to break very easily. So we're not really going to look at the m-1 peak. So actually, the fragment peaks that we're interested in are the ones that don't just involve removing a hydrogen. And you can see, actually, there are only two of those in this case. Okay, so suppose we have our molecular ion here. It's got lots of kinetic energy and it falls apart, and let's suppose this is the bond that breaks. Okay, so we break that bond open, so we're going to get two fragments. So we're going to get C2H5 and we're going to get OH. Now one of them, but only one, is going to have a positive charge because there is one positive charge in the molecular ion. The question is which one? And the answer is that it depends in part on the relative stability of the two ions. So if one was much more stable than the other, it would go almost always to that one. Sometimes though it's much more random, and you know, sometimes it goes one way, sometimes it goes the other. Now the important thing to remember is that when you see a peak in a mass spectrum, that doesn't just come from one molecule, or rather one ion. It comes from you know, thousands of trillions of ions. So it's just a case that you know, if it was, say, 5 times as likely that this gets the positive charge compared to that one, what you would see is 2 peaks, but this peak would be 5 times as big as that one, because you know, 5 times as many fragmentations would result in that being the positive charge rather than that one. But it's perfectly possible to see both peaks unless one ion is just overwhelmingly more stable than the other one. So we could get this, we could get this, and we can look in the spectrum to see if they're there. So C2H5, if you add that up, gives you an MR of 29, OH gives you an MR of 17. So that would mean that we would expect in the mass spectrum to get an M over Z of 29 if this fragment is formed, M over Z of 17 if this one is formed. And you can see the 29 peak is there. And that's probably due to that fragment being formed. 17 peak, on the other hand, is not there. Or at least it's not there as a peak of any convincing size, which suggests that if this fragmentation happens, it nearly always goes in that direction rather than this one. Okay, but again, remember, not all the molecular ions that are formed will do the same thing. Some of them might break there to give the 29 peak, for example, that we've seen, but some of them might break here instead. So another possible fragmentation is this one, where it breaks there. So again, we can think about what we could get. So we could get CH3, or we could get CH2OH. And again, when it fragments, each individual molecular ion will give a positive charge either on this one or on this one. But different molecular ions may give different fragmentation patterns. So it's possible that sometimes you get CH3 plus and sometimes you get CH2OH plus. So again, it's worth looking for both fragment ions in the spectrum. So this would give an M over Z of 15, and we can see there is a peak at 15, which is consistent with CH3 plus being formed sometimes. This gives an M over Z of 31, and we can see it's a much bigger peak, and that suggests that this fragmentation happens, and that when it happens it's more likely that you'll get CH2OH plus rather than CH3 plus, but that doesn't always happen. Okay, so we can make sense of some of these fragment peaks, not all of them. Some of these little ones especially very difficult to interpret, and generally you'll ignore the smaller peaks. It's tall ones like that that sometimes can be really useful in getting some clues about what the structure is. So in question 5 we have a different alcohol, and again what it wants us to do first of all is to figure out what the molecular formula is. And the way we do that, as before, is by looking for the molecular ion peak, which is that one, sometimes written as M plus for short, molecular ion peak, and that, remember, is the intact molecule just minus one electron to give it a positive charge. And the significance of that peak is that M over Z is equal to 60, which means that the MR of the compound is also 60. Okay, so you need to get used to identifying the molecular ion peak as the one furthest to the right, ignoring sometimes you can see the little C13 satellite there. On that one it's so small you can't really see it, but that's often there. So ignoring that one, it's the peak furthest to the right with the biggest M over Z value. And this is what you do with it, and make sure you explain clearly that that's what you're doing. So what do we do with that? Well, we know it's an alcohol, so we know it contains OH, which has an MR of 17, and 60 minus 17 is equal to 43. So if our alcohol is ROH, that bit has an MR of 43. And again, it's a case of just figuring out how many carbons that's going to be. So if it was 2 12s are 24, so that would have to be C2H19, and that's obviously impossible. There's far too many hydrogens there, so that's not an option. C3, 3 12s are 36, so that would be C3H7, and that looks very sensible. 4 12s for C4 would be 48, so that's too much. So it's got to be C3H7OH. But remember, the question asked for the molecular formula, so although that's how we worked it out, the answer you have to give is C3H8O. Don't forget you have to lump all the hydrogens together. So it's a 3-carbon alcohol that we're looking for. Now in the previous question, once we knew what the molecular formula was, it was obvious what the alcohol was, but that's no longer the case here. Because we have a 3-carbon alcohol, we can have propan-2-ol, or we can have propan-1-ol. So those are the 2 possible alcohols. Obviously the molecular ion peak doesn't distinguish them because they're structural isomers, so they have the same MR, same M over Z for that peak. So what we're going to be interested in is whether that fragment peak, possibly any of the other ones, but as I say, you've got to be very careful with smaller fragment peaks. It's those well-populated ones that nearly always come just from breaking one single bond. The question is whether we can use that peak to distinguish between the 2. So again, we can do that just by going through and looking at what fragmentations we might get. So if we do that for this one, if you break it here, that could give you CH3 plus, which would give you an M over Z of 15, or it could give you CH3 CHOH plus, which would give you an M over Z of 45. So neither of those corresponds to one of those tall peaks. You can actually see a smaller peak at 45, so maybe, doesn't rule it out, but it doesn't explain the 31 peak. Other molecules might break that bond, but of course this bond and that one are the same, because that's just that atom to CH3, and so is that one, so breaking here is just the same thing. If we break here instead, because some molecules might do that, then we would get OH plus, which would be 17. So that doesn't help us. And we would get CH3 CH3 plus if we got the positive charge on this fragment, and that comes in at 43. So again, it doesn't explain the fragment at 31. So those are the only possibilities. Other than that, all you'd be doing is chopping off single hydrogens, which would give you that peak at 59. But none of these fragmentations is explaining the peak at 31. So we start to have doubts about this. And so now we look at this. So again, we could break the OH off. And obviously that's going to have the same effect as it did up there. We could get OH plus at 17. And we could get CH3 CH2 CH2 plus, which comes in at 43. So those don't help. If we break here, we could get CH3 CH2 plus, which comes in at 29, and again, yeah, that peak's there, but it's not this one that we're really interested in. Or we could get CH2OH plus, and that does have an MR of 31, and therefore would give a peak with an M over Z of 31. So that fragmentation to give you CH2OH plus could explain the well-populated peak at 31, whereas if it was propan-2-ol, none of the plausible fragmentations could explain that. So that's strong evidence to support the idea that this is more likely to be propan-1-ol than propan-2-ol, because you can explain the 31 fragment here as that, you can't explain it there.